Okay, so let's do another example with friction. So this would be similar to something you've seen before, and that is you've got a mass M, okay, sitting on a surface, hanging mass little m, and now let's say there's some kind of static friction here. And so let's say that big mass M is 2.65 kilograms. And you start adding mass to little m, and then nothing happens, but when little m becomes 573 grams, all of a sudden it starts moving. So that means that up until that point, it was okay. At that point, that's the limit right there. Okay. So, we can say, we've done this several times. You put 573 grams on there. Sometimes it moves, sometimes it doesn't move. A gust of wind hits it, it starts moving. Okay. So that means that is your critical amount. If you put more than that, it definitely moves. So that gives you the maximum static friction. Because you notice what's happening. Free body diagram for the hanging mass. We got mg down, tension pulling up. Free body diagram for the mass on the surface. We got tension going this way. We got static friction this way. We got normal going up. And we got big mg pulling down. So we know that the normal force is going to be equal to big mg. Okay. And so now what's going to happen here is that the static friction, okay, we know static friction is going to be equal to tension, okay, if it's not moving. So if it's not moving, and only if it's not moving, static friction equals tension, okay, and so the tension has to equal little mg if it's not accelerating, okay, because the sum of the forces have to equal to 0. Now, the frictional force is also equal to mu sub k times the normal force. So if we put all this stuff in here, mu sub s times the normal force. So we put all this stuff in here together, then what we find is that mu sub s big mg equals little mg. Now this is the maximum that it can be. So the frictional static friction is going to be less than or equal to mu sub s mg. Okay, so so the frictional force will always be equal to little mg if it's not moving. So it doesn't matter what little m is. It's when little m, when it reaches 573 grams, that's the maximum it can be. So the frictional force will always be this up to that point, and at that point, the frictional force is equal to that. Okay, so we can do algebra, the g's cancel, and so the static friction is going to be equal to little m over big M, so that'll be 573 grams over 2.65 kilograms. So that's going to be 0.573 kilograms divided by 2.65 kilograms. So mu sub s is going to be 0.216. Okay. Now, let's say we had the same problem. Got m, little m right here. Got big M, got friction here, and so let's say again big M is 2.65 kilograms, little m is 573 grams. So it's right at that critical point. And then what happens is there's a little gust of wind, and that's all that it takes to start this moving. So now that starts accelerating this way, that starts accelerating that way. Once it starts, it doesn't stop, because when it starts, we have static friction was 0.216, but once it starts, it's no longer static friction. Then it becomes kinetic friction. And so kinetic friction is almost always less. Well, this friction here was necessary in order to hold it. So if a little gust of wind moves it a tiny bit, now we're in kinetic, and now this is not going to hold it, and so it's going to start accelerating even if we don't change the mass. So, free body diagram, big M, we got tension, we now have kinetic friction, we have normal, we have big mg. For the little mass, the hanging mass, we got mg, we have tension. But now we know that these are both accelerating. So our equations now are going to be that mg minus t equals ma. So sum of the forces equals ma. For the other one over here, tension minus F sub k equals big Ma. Well, F sub k is mu sub k times the normal. Well, we know that the normal is going to be big Mg for this problem. So that equals Ma. Okay, so now we just put our equations together. So we add the two equations. So Ma plus little ma, okay, and that's going to be T minus mu sub k mg plus little mg minus t. So the t's cancel. We do some algebra, and A is going to be m minus mu sub k big M times g divided by M plus M. Okay, so you start putting in all those numbers in there, and what you come up with is 0.235 meter per second squared, or 23.5 centimeter per second squared. I'd take either one of those. So there we have this problem right here, similar to what you've seen before, except now we've included friction into it.